So, in the interest of time, I'm just going to start the program so that as students and other key personalities join in, uh, they'll be right in time for both the inaugural address of Dr. L.K. Sharma and the main presentation of Dr. Jaideep. Good morning, Jaideep sir, scientists from NASA, Florida, and participants from USA. And good evening to Dr. L.K. Sharma sir and participants from India. My special welcome to Dr. Komati, chairperson of the Computer Society of India, Chennai chapter, and other friends from various organizations. On behalf of Explore the Space, I'm pleased to have this opportunity to welcome you for this webinar on a highly interesting topic, James Webb Space Telescope. We welcome participants from 25 plus engineering colleges, engineering and science colleges from cities including Chennai, Coimbatore, Puducherry, Mangalore, Bengaluru, Dharwad, Hubli, Thane, Vijayawada, Guntur, New Delhi, Varanasi, Aligarh, Purja, Mumbai, and Kolkata. That's about the registrations. We have 20 participants who have logged in now. I'm sure the numbers are going to steadily increase. This is part of the program series called Indo-US Youth Space Talent. That was a series inaugurated by India's celebrated space scientist and space technology leader, Dr. Kiran Kumar, former chairman of ISRO, way back in July 2023. So from July 2023, we've been organizing events bringing together students and experts, both from India and United States of America. The key objective of Indo-US Youth Space Talent is to motivate youth in India and USA to pursue careers in STEM and space exploration, encourage new collaboration in space industry, to promote space entrepreneurship and startups, encourage women entrepreneurship startups, new avenues for cooperation between India and USA, and to conduct programs in university campuses in India and United States of America. The previous editions had participants from University of California, Davis, University of Florida, IIT Madras, and Thakur Institute of Aviation, Mumbai. On today's specific program, the James Webb Space Telescope, friends, is an engineering marvel, and we will have the celebrated scientist from NASA, Dr. Jaideep, to speak in detail about that. The James Webb Space Telescope is a large infrared telescope with a 6.5 meter primary mirror as diameter, studying every phase of the history of our universe. The engineering of JWST is simply breathtaking. Just in comparison, the James Webb Space Telescope is 1.5 million or 15 lakhs kilometers from the Earth's surface. For the participants who may be interested to know, AstroSat is India's first dedicated space astronomy telescope that was launched way back in September 2015. And the AstroSat telescope is at 650 kilometers from the surface of Earth. As Jaideep mentioned, these two telescopes are meant for two different things. They are meant for two different things, but it would help us to comprehend about the size and the bigness of what we are talking about. On the two eminent gentlemen who are here with us today to present a fantastic program, it's actually the honor of, we are very fortunate to have someone like Dr. Jaideep Mukherjee. This is the 12th program that Dr. Jaideep Mukherjee is doing for Explore the Space. Ever since we came in contact with Jaideep sir way back in 2018, Jaideep is a great friend of science dissemination. So that's the point of contact, and that's the point of interest, which makes us to request Jaideep every time. And Jaideep is someone who shares knowledge so willingly, so frequently, and we have talked it at many places that we would like to see more men and women like Jaideep emerge so that science spreads much faster. Thank you, Jaideep. Jaideep is the director of NASA Florida Space Grant Consortium. Thank you. It's an association of 17 public and private Florida universities. The consortium also includes all of Florida's community colleges, as well as the Astronaut Memorial Foundation, Space Florida, and Kennedy Space Center. Interestingly, Dr. Jaideep Mukherjee received his bachelor's degree in physics from St. Xavier's College, Mumbai, and master's degree in physics from Mumbai University before proceeding to the US, where he did his MS and PhD degrees in astronomy from the University of Florida. Currently, he is serving on the board of directors of the National Space Grant Alliance and is a member of the Commercial Space Operation Advisory Panel at Embry-Riddle Aeronautical University. The main interest of Jaideep includes binary stars and STEM education. Jaideep is married to Madam Srila Malik, who is also part of NASA, and they both reside in Titsuvili, Florida. Welcome to the program, Jaideep.
Thank you.
Friends, I have pleasure in introducing to you Dr. L.K. Sharma, who was very recently the president of Indian Ceramic Society and currently the chairperson of the India chapter of the American Ceramic Society. Dr. L.K. Sharma is the CEO of Mahamana Ceramic Developmental Organization. He is a member of the International Ceramic Federation and a visiting professor of Delhi Technical Campus, Greater Noida, a visiting professor of PDA College of Engineering, and a fellow of Indian Institute of Ceramics. He was formerly the chief scientist and scientist in charge of CSIR, CGCRI in Kurja. As I mentioned before, Dr. L.K. Sharma is a great connector of people, and he brings together people to conduct events and programs like this. Dr. L.K. Sharma, we are really lucky and fortunate to have someone like you to have agreed to inaugurate this program. We have about 32 participants who have signed up now, and we will continue with the program. And may I request Dr. L.K. Sharma for your inaugural speech, please.
Thank you, Venkat, for great introduction.
Thank you,
and
sir.
Good morning to Dr. Jaideep from Florida, and good evening to all participants from India. So, dear friends, because so many assistant professors and professors also from IIT BHU or IIT Chennai are likely to join. So I'll call that dear friends. Students are there and all other participants. It's a great moment that Mr. Venkat has with his colleague, Mrs. Sumitra, has organized the webinar on unveiling the universe through this James Webb Space Telescope. It is totally a new, you can say, initiative for you to know about new equipment and gain knowledge. You will find so many unimaginable facts which our past generations missed, and we are lucky today that we'll know each and everything about that. All this will be taught, I can say, as a teacher by Dr. Jaideep, because whichever is new in our life, and if someone teaches us, so I will call that he is a teacher for us. Dr. Jaideep is the director of NASA Florida Space Grant Consortium in USA. So I'll not talk much. I am being the live member of Explore the Space. Would like to welcome Dr. Jaideep to this virtual platform, and on behalf of Explore the Space, I welcome Dr. Jaideep on behalf of Indian Ceramic Society as immediate past president of that, and also on behalf of the American Ceramic Society as founder chairperson of the India chapter of the American Ceramic Society. I welcome you, sir, as CEO on behalf of Mahamana Ceramic Development Organization and on my personal behalf to this virtual platform. Just for the knowledge of all the participants, because so much Venkat also has covered. So if you want to know about universe, like planets and stars, etc. So this Webb Space Telescope is the answer, and since 2002 only, in this 21st century, this telescope was named as this. What you know that James Webb on the name of the second administrator of the NASA, which is we are whole world is proud of NASA, and where Dr. Jaideep is there. So second administrator was Mr. James Webb. On his name, it has been named. This telescope has been named since, and he was there in 1960. Almost 20 feet in size, six 6,000 kilograms weight, lot of infrared cameras which can detect the object through heat radiation, even if it is hidden in the dust. It will even inform us about atmosphere where we can sustain life. So I will not take much time. Dr. Jaideep will cover much more in depth. So with this, I am done and welcome everyone to this virtual platform. Now, I think if nothing else, stage is yours, Dr. Jaideep. Thank you very much. Thank you.
Well,
Thank
thank
you.
you, Dr. Sharma.
Thank you so much, Dr. L.K. Sharma ji. Now, can I request Dr. Jaideep sir for your presentation, please? The number of participants are growing in number. We have about 35 now, but I would request you to start your presentation, please.
Yes. Hold on. Let me share my screen.
Yeah.
How long do I have? So I'm
Uh,
sure I'm doing.
Jaideep, you have an hour, 1 hour, 60
Okay,
minutes.
okay. Okay, can you see my screen?
Yeah.
Okay, great. Well, thank you, Dr. Sharma and Venkatagiri. Greetings from Florida. It's very nice and sunny, not as hot as Mumbai, I'm sure. But what I wanted to do was to give you an idea about the James Webb Telescope, both from an engineering point of view and from an astronomy point of view of what it has observed. I guess most of the students and participants are engineers, but I also wanted to talk about some of the amazing discoveries that the James Webb Telescope has so far made in the last couple of years. So that's the title of the topic. It's unveiling the universe. But I wanted to give you briefly why we are using the James Webb Telescope, why we are studying these objects, and then talk about the engineering. I'm not an engineer, but any space mission, and these are for the students. If you want to take part in a space project, it's mostly driven by science, but most of the work is done by engineers. So for the James Webb Telescope, the way it was done was there are some science priorities, and to achieve those goals, science goals, you have to come up with this telescope and instruments. And so these engineers play a big role in space missions. But and I have seen this from big missions in NASA and from small groups working together in colleges and schools. Especially when you're in college, if you're an engineer or if you're going as a scientist, you think differently. Your approach is different. So anyone who wants to take part in space projects must understand that you have to respect each other. So if you are an engineer, you have to listen to the scientist and vice versa. And if you don't do that, the mission will flop. So you want to join industry, you want to join academia, you have to remember this. So I'm going to start with a 2-minute, 2.5-minute video, which is kind of a teaser trailer, which tells you of the James Webb Telescope. I don't have to say anything. There is some sound, but it's a good way to give an introduction on the James Webb Telescope. So that gives you an idea of what I'm going to talk about. I'll elaborate on every point in that short video. So the question comes, why James Webb Telescope? Why choose that as a major project? So what happens is every 10 years, you have a group of scientists and astronomers to get together to decide what are the priorities for the next decade. And in 2010, they had identified some big science questions in astronomy for the decade of 2010 to 2020. So these are the questions, right? Where did we come from? How did we get here? Are we alone? So the questions that we answer in astronomy, they're more than science questions. They're questions that get to the heart of what it means to be a human being. And these are the questions that humans have asked and sought the answers since we have begun to ask questions. So, if you go back 2,000 years ago, people wondered, are we alone? For them, alone means, is there someone else 100 miles from here, 200 miles from here? But as years go by, as we expand our horizons and knowledge, for us, are we alone means, are we the only planet which has intelligent life? Or are there other planets in a galaxy or in other galaxies? Where did we come from? And how did we get here? So these are the questions that we all want answers to. And because of that, to answer those questions, we come up with this scenario. So the history of the universe. So the universe started with something called the Big Bang about 13.6 billion years ago. And then from there, you had the first galaxies forming. The galaxies are nothing but a collection of billions of stars like the sun. There are about more than 100, 200 billion galaxies in a universe. Each galaxy has over 100, 200 billion stars. So for the Big Bang, once the Big Bang of the universe was formed, the first galaxies formed. Then the galaxies evolved. Some of the galaxies actually combined and formed bigger galaxies. As the galaxies formed, new stars were forming within these galaxies. Some of these stars, when I say some, I say more than 70, 80% of these stars have planets around them. Okay? We think that there are more than 5 billion, a lower estimate, 5 billion planets just in our galaxy. So, and if you have planets, are they inhabited? How did life form? So this is the whole cycle. This is what we want to answer. And the James Webb Telescope is going to answer every aspect of this story. But to understand this, to get the whole story, we need a space telescope. The reason is that if you have a telescope on the Earth's atmosphere will block most of the radiation, mostly light and the infrared coming from these objects. So we need a telescope in space orbiting the Earth, orbiting the sun, like the Hubble Space Telescope. We need an infrared telescope, but I'll tell you why we need an infrared telescope in the next few slides. And then we need a telescope with a large aperture. The larger the aperture of the telescope, fainter an object we can see, and further back in time we can go to. So these were the requirements that we needed to understand the story of a universe. So I know a lot of you engineering students, and bear with me if I'm saying things that are elementary to you, but I'm not sure of my audience. I just want to give a quick background on the radiation, electromagnetic radiation, because it plays an important part in this story. So if you look at the top one, where we see different types of radiation, we start with radio waves, which are the least energetic, and we go all the way to gamma rays, which are the most energetic forms of radiation. Visible is what we can see with our eyes. Our eyes are detector for visible light. For all the others, we need telescopes and radio telescopes and other kind of detectors to detect the radiation. But what is important, if you look at the top graph out here, it shows radio waves can go through the Earth's atmosphere, so we don't need a radio telescope in space. But microwave and a part of the infrared are blocked by the Earth's atmosphere. most of the ultraviolet, X-ray, and gamma rays are blocked by the Earth's atmosphere. The visible light goes through unless there are clouds, and radio waves can go through clouds if need be. So these are the restrictions of the electromagnetic radiation. So to see infrared, to detect infrared, detect ultraviolet, X-rays, gamma rays, we have to go above the Earth's atmosphere. And the lower graph out here will give us the temperature. So as I said, if your gamma ray is coming from an X-ray is coming from an object which are very, very hot, a lot hotter than the sun. If you have something temperature about 9,000 centigrade or 10,000 Kelvin, that kind of corresponds to stars, and that's where you get the visible light that we see with our eyes. But as you get colder, as you go to gases and clumps of gas, they're mostly emitting the radio and in the infrared. We are more concerned with the infrared, and I'll tell you again why we are more concerned with the infrared right now to understand the beginning of the universe. But this gives you an idea of the electromagnetic radiation and the different types. The other thing, again, I apologize because I know most of you engineering students, this might be really trivial to you, but one thing which is going to be important here is the Doppler effect concept. And you know about Doppler effect in terms of sound. So when I'll give an example. So you have a train approaching you and then going away from you, and see how the pitch changes. So that's the Doppler effect, is this change in frequency, and that is shown here in this. So you have this source is emitting sound waves, but if the source is moving either towards you or away from you, if it's moving towards you, look how these waves are kind of coming closer and closer together. But as you go further away, they're actually going away from each other. So that's what the Doppler effect is in the case of sound. But in the case of light, if you have a light being emitted by an object, say a faraway star, but for some reason the star is coming towards you, then what happens is the light waves are kind of squished and they're bluer in color, and we call them blue shift. But if the star is going away from you, then the waves are kind of stretched, and we call it redshift. We call it redshift because the red has a longer wavelength than the blue light. So wavelength is nothing but the distance between the crest of two waves. So red light has a longer wavelength and blue light a shorter wavelength. So that's a Doppler effect in terms of light. Why am I telling you all this? Because of something called the cosmological redshift. The universe started with the Big Bang. And I don't have time to explain you everything about that, but it started with the Big Bang, and we know from various observations the universe is expanding. And as it expands, the space between galaxies are expanding. So look what's happening. You have a galaxy very far away and say it's emitting X-rays because it's very, very hot. As the universe expands, this X-ray wave is stretched. And right now, at this moment of time, any radiation that left 13.5 billion years ago have been stretched to the infrared. And that's why we want to have an infrared telescope if we want to see what stars and galaxies look like 12 billion years ago. So that's the reason for having an infrared telescope. Of course, if you want to look at faint objects, we need a big telescope. And if you want to detect infrared, you have to go above the Earth. And that's what the Hubble telescope was built. Here's another example of light from the visible galaxies, gamma rays are stretched all the way to the infrared, and we call it redshifted. If you look at the sun, most of the sun's energy is just visible light. But if you have an infrared detector that can detect infrared radiation, for example, our body emits infrared radiation. So here's an example of a person holding a match, and that's an infrared picture. Now the eyes are colder than the rest of the body, so it's bluer in terms of temperature. But because this is very hot, it's brighter than the infrared. Same thing with the cat. These are footprints from a person. again in the infrared. So with the infrared, you see something that you cannot see with the visible light. Here's another example of two animals, and you look how they look in the visible, but then again in the infrared, we see something different. Same thing with objects in the universe. If you look at the sun, if you just what you have seen is just a picture of the sun that is emitting visible light, but the sun emits X-rays, ultraviolet, radio, and if you look at the sun with different telescopes, it looks different. That's why in astronomy we use different types of telescopes to study the universe. But here we are concentrating on infrared light. So finally, here's the James Webb Telescope. It's a large infrared telescope. It's about the diameter of the mirror. The main mirror is about 6.5 meters. It's a successor to the Hubble Space Telescope. It's very international with USA, Europe, and Canada. Unfortunately, India was not a part of it. This was 20 years ago. Right now, India is a part of the Artemis mission, so they're going to play a big role in that. The senior project scientist is Dr. John Mather. He is a Nobel laureate. The total cost, this slide was made a few years ago. It's more than 11 or 12 billion dollars. So it's very, very expensive. And it was launched on December 25th, 2021 from French Guiana. And I'll tell you why we chose that to launch the rocket. Here's a model of the rocket. Look how big it is. This is a full-scale model. And I'll talk about each of these parts. This is called the sun shield. This is the mirror. And these are all the scientists and engineers working, at least at the headquarters in DC. This is in Maryland. Here is the international component. USA has 2 science instruments, then they provide the rocket on the launch. The Canadian Space Agencies have 2 science instruments, and NASA is in charge of the mission and in the observatory. This is the main parts of the telescope, and I won't go and talk about every detail, every single part, because that'll take a lot of time. But I'll talk about the main parts. One of the main parts is the main mirror, and the other one is something called the sun shield, because without that, this whole telescope will not work. The spacecraft bus has all the instruments required to operate the spacecraft. And right here, you have all the science instruments, all the detectors to detect the infrared light. The star trackers are there to actually look at the stars and find out where the Hubble Space Telescope is in space in relation to the stars. So let's talk about the mirror, okay? Now, you cannot build a very huge mirror. If you try to build a mirror 6.5 meters, it'll sag at the middle. It's not possible to build a big mirror. So even the large telescopes on Earth are not one single mirror, but the number of mirrors built together. The same thing with the James Webb Telescope mirror. It's not made up of one mirror, it's made up of a number of small mirrors put together as one main mirror. And look how large it is compared with the Hubble primary mirror. But remember that this is a 6.5 meter telescope, okay? The mirror is 6.5 meters. You cannot afford to have a rocket which is 6.5 meters wide. That makes it a huge rocket with more fuel is more expense and so on. So engineers had to come out with a way that they could fold this mirror and fit it into the rocket. So apart from the fact that you cannot have a large mirror, another reason for using multiple mirrors is because they wanted to able to fold it and put it inside a rocket. The other question that comes up is, if you look at all the different segments, why aren't the segments circular? Why are they this shape? And the main reason is if you have each of these segments circular, then if you try to fit them together, there'll be gaps between the segments. You don't want that. This is the best configuration where you can fit different segments without having any gaps in it. And then this whole thing acts as one circular mirror. You don't want a circular mirror is the best one because you can focus the light on the central part of the detector. If the mirror is not circular, if it is elongated, then even the image is going to be elongated. If it is square, then the light from the target object will not focus to the middle of the detector, but all around it. So a circle is the best formation, and the only way to have different segments without having any gaps between the segments is to have this shape. And it's coated in gold. The reason it's coated in gold because gold is a very good reflector of infrared radiation. Now, I'm not talking about lots of gold. It's a very thin layer of gold. And of course, again, another thing you have to consider is you cannot afford to have a very heavy telescope. So you have to use a material which is light but also very strong. And beryllium was the one which is strong and very light. So astronomers and engineers use beryllium to build the mirror of the telescope. And this gives you the light gathering power. The light gathering power depends on the area of the whole primary mirror. And look at the light gathering power of the James Webb Telescope. It's tremendous compared to the Hubble Space Telescope or Spitzer. Spitzer is an infrared telescope, but it's very, very small in size. So it cannot detect everything. The James Webb Telescope is large, it's light, great light gathering power. So you can look at faint objects formed just a few million years after the Big Bang. So that's the difference between the Hubble Space Telescope, the James Webb Telescope, and Spitzer. Main thing is the size. The other thing is you can look a lot along the infrared portion of the electromagnetic radiation. So again, you have 18 hexagonal segments made of beryllium, the lightweighted, coated with gold because of high infrared reflections. See, the other thing is, once you have all these 18 mirrors, you have to align them in such a way that they focus the image from an object. And they're all done by having small motors behind each of these segments called actuators. And they provide minor adjustments to each of these segments to a scale of nanometers. So a paper is about 100,000 nanometers. Just talking about a paper. Here is providing adjustments on a scale of nanometers, not hundreds, but of nanometers. So these are amazing motors which are able to do that. And in a few slides from now, I'll show you an animation of how it kind of moves everything to focus an object. But this is where I have my admiration for engineers. Without all these things, scientists will not be able to observe anything if the engineers cannot come up with these different ways of building the telescope and the instruments. So the telescope, you have the main mirror telescope. You also have to have a secondary mirror because light will come and infrared radiation will come and hit the primary mirror, will hit the secondary mirror and go through here to the instruments, where the instruments will make the measurements. But remember, it's infrared. Infrared works at very low temperatures. So if the telescope is pointing towards the sun and sunlight is hitting the telescope, no infrared radiation. There's no way you can detect infrared radiation. So you have to have a way of trying to block the heat from the sun or sunlight, also from the earth and the moon. And that is done with what is called this the sun shield out here. Again, this is a great piece of engineering. And let me elaborate on the sun shield. Here's an example of the sun shield. It's made up of 5 membrane or 5 layers. Okay. In between the layers, you have vacuum. And what happens is when sunlight hits the top layer, some of the heat is conducted through the first layer, but then you have a vacuum. So there's not much of a conduction. As you go from first layer to the second layer to the third layer to the fourth layer, most of the heat is gone, is deflected away. Also, if you look at the mirror there, it's coated with aluminum because that is a very good reflector. And also it has what is called doped silicon. A doped silicon is nothing but silica where you have added some other material to make it electrically conductive. Because you want the membranes to be electrically ground with the rest of the James Webb Telescope. Otherwise, there'll be electric charge building up. So you can't afford to have that. So each of these mirrors are coated with this aluminum and and there's doped silicon. And again, you have 5 layers, as I said, because you have this vacuum. If you had one thick membrane, then heat can conduct through the membrane itself. But if you have this 5 layers and you have this vacuum in between, then the heat is all dissipated off. And here it gives you an idea. Here are the two sides of the James Webb Telescope. You have the mirror, you have the hot side, we have the sunlight heating. Look how hot it is, 85 degrees Celsius. But as it goes to the 5 meters, most of the heat is dissipated. And what you have on the other side is very, very cold, minus 233 degrees Celsius. And that's the temperature you would need for this science instruments to work. So without the sun shield, the instruments won't work and nothing will work. So the sun shield plays an absolutely important part in this for this telescope. And here, as I said, you have the sunlight coming in. Some of the heat is conducted through, but then as you go from the first membrane to the second, third, and fourth membrane, the first membrane is flat, but then the second, third, and fourth are a bit curved up a bit because you won't allow the heat to just deflect away from the sides. So as you come to the 5th layer, there's almost very little heat going through. And I think this is amazing that, I think the name of the material is, I think, Captain or something. I'm very bad with names. But that's a material that DuPont company came up in the 60s. And they have used this to for the sun shield. So again, I'm going back to the same picture. You have the sun shield, you have the mirror, you have the secondary mirror. This is called the spacecraft bus, which has most of the control machinery. I talked about the star trackers, which is small telescopes that are used to you look at star patterns, then you find out where you are with respect to the sun star patterns. Of course, you need an antenna to send the data back to the Earth. Don't make any of those marks. That doesn't make sense. So please don't draw on the screen. Here's the secondary mirror, primary mirror and the secondary mirror. I've seen this at students in India. I don't know why they do that. Why do you do this markings on the screen? It becomes tough for the speaker to talk. So please don't do that.
I'm sorry about that. I'm sorry, JD.
It happens all the time, so it's okay. Don't worry. It's always 1 or 2 persons doing it. It's not the whole group. And here's the science instrument module, which contains all the instruments. Again, just to not to save time, I will not talk about the instruments itself, but this just animation just gives you a quick, if it works. It gives you a quick idea of the instruments, which is behind the sun shield. So you have the mirror, light from the mirror comes and hits, and here you have the instruments at the back. There are 4 different instruments measuring the infrared. So that's what you see behind the primary telescope. And here are the 4 cameras, 4 instruments. One was from the University of Arizona, one by NASA, one by JPL, run by the Canadian Space Agency. If you don't mind, I'm going to just stop sharing and I'm going to get this up again so this screen does not come. Just give me 1 second. I'm going to stop sharing and again start.
Yeah. Yes, please.
And I'll start again.
Yes, please.
And again, it's a plea to the few participants who are trying to draw on the screen. It affects the way I talk and I lose my continuity. That's why. So just give me 1 second. I'll go back to the slide.
Yes, please. I'm sorry about that, JD.
No, it's got nothing to do with you. It's got nothing to do with you. This happens quite a lot, I know. 1 second. Yeah, there you go. There you go. So I talked about the 4 instruments. Now, again, I'm only showing a small part. That a lot of testing is being done. Remember, this telescope, the instruments have to be in a rocket. The rocket is being launched. As the rocket launches, a lot of vibration, a lot of sound. So you have to test to see that as a result of the vibration, the telescope is not affected. So you have what is called a shaker table at the Goddard Space Flight Center. And they shake the table to simulate the forces the telescope will experience during launch. So the table is being shaken 5 to 100 times a second. And that mimics the vibration you get during a launch. Also during a launch, there's a lot of sound. And they're trying to test to see that it does not, that the sound will not affect any of the instruments on the telescopes. Again, this is just some of the things that you have to test to be sure that the telescope works. Now think about this, and you'll see why I'm saying this. But this telescope is not orbiting the Earth, because if it was orbiting the Earth, if something went wrong, you can send some kind of a rescue ship and repair, as it did with the Hubble. This telescope is about 1.5 million kilometers away from the Earth. If something goes wrong, one small thing goes wrong, you have lost the whole telescope. Nothing will work, and we cannot rescue it. So everything has to work fine. So you have to test it all the time. So I've talked about the telescope very briefly, and there's a lot more to it. Let's talk about the launch. So the launch took place from French Guiana. Why French Guiana? Because we wanted to be as close to the equator as possible, because for a point at the equator, that point is spinning faster than a point, say, above in near the poles or somewhere in between. So if you launch a rocket near the equator and the Earth is spinning from west to east, then the rocket takes the speed of the Earth's rotation itself. If you want to launch a rocket in the other direction, it'll be against the spin of the Earth. So you have to put more fuel in, put in more speed. That's why most of the launch pads are as close to the equator as possible. For NASA, we are at Florida, which is very close to the equator. Hawaii is closer to the equator than Florida is, but Hawaii is an island in the middle. In India, look where the launch pad is, as south as possible. Again, the launch pads are very close to the shore because you don't want a launch going over land. If something happens to the launch, then debris will fall over land. So all the launch pads, or most of it, are in near the coast, except maybe Russia and China. And Russia is in the middle of nowhere, so if something goes wrong, it won't fall over a populated area. And China, it's a bit different. They don't follow protocol. They are launching from even near populated areas, and I've known of first stage of rockets coming and hitting near towns and cities. But most places they try and launch near the coast. So here's in French Guiana, it's closest to the equator. The European Space Agency has a launch pad there for the Ariane rocket that they have used for launches. And that's a picture of the launch pad in French Guiana. It's a heavy launch vehicle. Again, people who are interested in numbers, it gives you the height, 150 feet height. It's very, very heavy, so more than 700,000 kilograms. And it has 2 stages. And look, so here's a diagram of the rocket. But look, you have to fold the mirror. You have to fold it so it could fit into the rocket itself. Because if you put the whole mirror, then this rocket would have been wider at the top, and that would have made it a larger rocket. It made it heavier and more expensive. So that's why the mirror had to be folded. Now, this is like a 4-minute video, but I think this is the best video because it's an animation which shows all the different things that they had to do before the James Webb Telescope reached its point of orbit. So watch this video. It's self-explanatory. It's a bit long, 3-4 minutes, but I did not want to cut it because I want to show you all the different things that has to go right for this operation to succeed. So Northrop Grumman is the company which built the telescope. Again, this is just an animation. It's a deployment sequence, deploying the telescope from the rocket. So this is after the launch. You look at the elapsed time on the top, and here on the left is how far it is from the Earth. So here the solar arrays are getting deployed to get power. It's only 40 minutes after launch. So now you release the antenna to communicate with the Earth. The mirror is still folded. And of course, you have to do corrections so that you're in the right orbit. So you have this initial mid-course correction. So you're almost towards the moon right now. So you have 2 days after the launch. They have gone past the moon. This is the farthest that we have sent a telescope so far, our object so far. Here's the sun sheet being deployed, one part. Again, if there was a hitch in one of these, the whole object is gone. So everything had to work, and all pre-programmed. So computer science students, hats off to you. I don't know how you guys do it, but all programmed. And this is the tower deployment. The tower is the main telescope, which will have the mirror. And those are the membranes that are being released for the sun sheet. So we have gone far beyond the moon right now. It's 5 days after launch. So again, these are parts of the sun sheet. You see, there's so many things that have to go right. So cryocoolers are instruments that can cool the instruments because one of them needs to be at a very low temperature. So we need like a helium cooler to cool it. So now these are the telescope, the main mirror being put together. So as it was folded, it's only unfolding it because that's the only way you could fit into the rocket. So now you're 30 days now after launch. You've gone far away from the moon, about 1.4 billion kilometers. You're coming very close to what is called a halo orbit around a point in space called the Lagrangian point. I'll explain that in the next slide. So here, this is exaggerated, but that's the orbit is going to make around that Lagrangian point. So I wanted to show you this animation just to give you an idea of the various things that had to be done before it went into orbit. So now the orbit itself. So if you look at the sun and the earth, the earth is about 150 million kilometers away from the sun. So the James Webb telescope is at one point in space which is far beyond the moon, and it's called the Lagrangian point, because at this point the gravitational force of the earth and the sun kind of balance each other. So if you can put an object out here, it requires very little fuel to orbit that point, and I'll explain that a little more in detail. But if you have any two major objects, say in this case the sun and the earth, then there are 5 points where the gravitational forces of the two objects and the orbital motion of another small object, they balance each other. So there's one point called the L1 point, where it is between the sun and the earth. And if you want to study the sun, you want to put a telescope out here because that's always look at the sun. And there is the Parker Space Telescope that NASA has, which is at this point, always looking at the sun. The L2 point is another point where the gravitational forces balance each other, but it's behind the earth. And the reason we want to use this point or not that point is because you want the sun to be blocked by the earth all the time. So this L2 point, as the earth goes around the sun, the L2 imaginary point is also going around the sun at the same speed as that of the earth. So when the telescope is at this point, as the earth goes around the sun, this point, this point is also going around the sun, but the telescope is orbiting this point out here. And because it's orbiting, it's not in the shadow of the earth and the moon. Because if it is a fixed point over here, then it will be always being blocked by the earth and the moon if the moon comes here. So it's actually orbiting this point over here. And as the earth goes around the sun, this point also goes around. So in fact, the James Webb telescope is orbiting the sun. So again, here's another example of the Lagrangian points. Now, these points are kind of what we call metastable, which means, like, for example, if you take a hill and you take a ball and you keep it on the top of the hill, then if you just make a small push, the ball can fall in either direction. But you have a very huge bowl and you put a ball in the middle of that bowl, then even if you make a small push, it won't go anywhere, it'll stay in the middle. These points, L4 and L5, are the stable Lagrangian points. L3, L1, and L2 are this metastable, which means that you have to give it a little force for it to go around. And that's what it does. You have a little fuel in the rocket, and the rocket is actually, and the telescope is actually going around this point. The orbit of the telescope around the L2 point is the same as the orbit of the same size as the orbit of the moon around the earth. So again, as I said, this is going to orbit the Lagrangian point. Again, this is exaggerated. So how do we get the data? So there are ground stations on the earth which are receiving the data from the James Webb telescope. I think they can download about 57 gigabytes of data each day. Maximum data rate is 28 megabits per second. It's not anything what we have here on the earth with the internet connection, but you're talking about deep and outer space. So that's the best we can do. And it takes about 5 seconds for the data to reach us from the telescope, or vice versa, because it's so far away. Again, we have these 3 what we call ground stations on the earth. One is in California, one is in Madrid, one is in Australia. And with these 3, one of them is always pointing towards the James Webb telescope. So we're going to always get data from the James Webb telescope. And as the earth rotates, one of these will be always getting data from the James Webb telescope. There is a control room in Maryland where they get all the data, and that's the control room of the James Webb telescope. So I talked of the telescope. I talked about the orbit and everything. And I have about 10 minutes. I'm going to talk about some of the observations. So now I'm not going more into astronomy and astrophysics. So here are the first observations. This is the first observation, and there are so many things that I can talk about in this picture, but I don't have time. First of all, the picture that you see is if you take a grain of sand and you hold it at arm's length, that's a part of the sky that this James Webb Telescope took a picture. It's actually a picture of a galaxy, of a cluster of galaxies. Each of these blobs that you see out here are galaxies. Each of the galaxies have about 100 to 200 billion stars. And there are more than 1,000 galaxies in this cluster. Again, imagine a grain of sand at arm's length. That's what you're looking at. But here's the interesting part. What you're seeing is light which left this galaxies about 4.5 billion years ago. It's so far away that light took 4.5 billion years to reach us. So we're going back in time. Now, as we go back in time, the radiation, when it left these galaxies, was very, very bright. It was in the X-rays and ultraviolet. But as the universe expanded and as the radiation reached us, it was more in the infrared. That's why we have the infrared telescope, so we can look at these objects, because the light right now from these objects have redshifted to the infrared. But here's the other interesting thing. If you look at these elongated arcs out here, this cluster of galaxy, 4.5 billion years away from us, acts like a gravitational lens, like a lens, magnifying lens. So the arcs that you see are actually galaxies far beyond this galaxy cluster, far, far beyond, 10 billion light years away. But because this galaxy cluster, the mass of the galaxy cluster acts as a gravitational lens, it magnifies those galaxies. And this is what Einstein had predicted. So this acts as a magnifying lens, and now we are seeing these galaxies. They're kind of in a stretch because of the lensing effect, but these are actually very far away, not like these galaxies. So here's another amazing thing. You're looking at one picture, but you're seeing light from galaxies tens of billions of years away. And if you look at the Hubble picture, the Hubble had taken a picture of the same area of the sky. It's a smaller telescope. It had to take an exposure time was 11 days to come up with that picture. The James Webb Telescope took less than 1 day exposure time. Now, remember, exposure time is you take a camera, you take a picture. Our exposure time to take a picture on the Earth is like 0.1 second, 0.2 seconds. More than that is going to saturate the lens, the film. But in the case of for faint objects, because they are so faint, you have to expose it for a long time to gather all the light coming from that object. That's why in astronomy you have long exposure times. So, but now for the James Webb Telescope, instead of having 11-day exposure time, you have 0.8 days. So that's the galaxy. The second was, here's another interesting one. This is a planet around a star like the sun, okay? Except the star and the planet about 1,000 light years away. This planet is almost half the mass of Jupiter. Jupiter is the largest planet in our solar system. We can fit 1,000 Earths inside Jupiter. That's a huge planet. But this planet that they found, this is an artist's conception, by the way, because we can't actually see the planet. It's so faint and so small. But this planet is half the mass, but it's about 1.2 times the size of Jupiter, but it is very, very close to the sun, to the star. So it's so close, it's about 1/9 the distance that Mercury is from our sun. This planet is so close, it takes about 3 days to make one orbit around that star. So you have an example of a very a big object, but very close to the star. And how do we detect it? We detect it because if you're measuring the light coming from the star, it'll be a straight light. But if we have a planet coming in front, it's going to block a part of the light, and that we see as a dip. And by studying the dip and how big the dip is, you can get an idea of the size of the planet. And that's what we did. We found the size of the planet by looking at the dip as the planet went in front of the star. Now, there's something called spectroscopy. Again, I'm trying to explain astronomy class in 2 minutes, but this animation will tell you how we can figure out the elements in the atmosphere of another star or planet around another star. So just bear with me and just watch this. It's a very good video. I think there is sound, but it explains how we can study the
How do we learn
atmosphere.
about a planet's atmosphere? How do we know what's in the atmosphere of an exoplanet? The majority of known exoplanets have been discovered because they partially block the light of their host star. This is called a transit. During a transit, some of the star's light travels through the planet's atmosphere and gets absorbed. The light that survives carries information about the planet across light years of space where it reaches our telescopes. However, the planet is very small relative to the star, so it is still very difficult to detect, which is why we need a big telescope to be sure to capture this tiny bit of light. So how do we use a telescope to read transit light? Stars emit light at many wavelengths. Like a prism makes a rainbow, we can separate light into its separate wavelengths. This is called a spectrum. Visible light appears to our eyes as the colors of the rainbow, but beyond visible light, there are many wavelengths we cannot see. Now back to the transiting planet. As light is traveling through the planet's atmosphere, some wavelengths get absorbed. Which wavelengths get absorbed depends on which molecules are in the planet's atmosphere. For example, carbon monoxide molecules will capture different wavelengths than water vapor molecules. So when we look at that planet in front of the star, some of the wavelengths of the starlight will be missing, depending on which molecules are in the atmosphere of the planet. Learning about the atmospheres of other worlds is how we identify those that could potentially support life, bringing us another step closer to answering one of humanity's oldest questions. Are we alone?
So I wanted to show you because this is the best way to explain to you how we can get the atmosphere. I'm going to skip this slide. But why this is interesting was when we found the spectrum of the molecules in the atmosphere of the planet, we found out of water molecules. We know there is haze, there are clouds. So again, life might not be possible because it's so close to that star, very, very hot. But here we have an example of a planet which has water molecules. So, if you're thinking about finding life elsewhere, there are a lot of candidates in our galaxy. Here's another example of an observation. This is called, it's called a planetary nebula. It's actually a star like the sun. When it dies, it ejects its outer layers. And if you see it face on, this is an example of what is called a planetary nebula. And this was taken with the James Webb telescope with 2 different instruments. Now, for example, if you take the sun, for example, as the sun gets older, in about 5 billion years, it's going to expand. It'll go all the way towards the orbit of Jupiter. It'll be a huge object. It's going to eject its outer layers, and the inner parts will be compressed to what is called a white dwarf, and that'll be the size of the Earth. So as the sun gets old and it dies, it's going to be compressed to the size of the Earth, called a white dwarf, while the outer parts are ejected away, and that's a planetary nebula. So here you see the planetary nebula face on. But in the inside, you see one bright object, and that's that star which ejected the outer layers. But if you have a better instrument, you can see it's not one star, but there are 2 stars orbiting each other. And that's the beauty of the James Webb telescope. And the brightest star eventually, again, is going to eject its outer layers. Right now, it's this faintest star which has been ejecting the outer layers, and that's all you see over here. Here's an example of a planetary nebula. Another example, when you look at James Webb telescope pictures, you always see these galaxies in the background, right here and right here. So that's a galaxy very far away, containing billions of stars. And here's an example of an animation of a planetary nebula in the last stage of its life. The outer parts of the stars is being ejected away. And there was this cycles of this ejection. And the inner parts is being compressed to the size of the Earth, say. And that's what you call a white dwarf. That's what's going to happen to the sun as it gets older. So that's a planetary nebula with a star in between. And that's what I showed you was the ring nebula. There are a number of such planetary nebulas in a galaxy. The other thing, this is a bit more on the artistic side, but if you're blind, say, okay, you cannot look at these pictures. There is a way that you can convert these different wavelengths to sound. It's not that these are emitting sounds, but these gases, the wavelength of the gases can be converted to sound. And if you can't see, you can hear how the sound changes as you have different gases emitting those light. So let's hear that. What's this? So different gases, different, when they're converting it to sound. So you see, again, this is not scientifically very important, but it helps the others to actually kind of understand how, if we tell them that the different sound corresponds to different gases, then they'll know more about it, especially if you're blind. Here's another example of interacting galaxies. It's called the Stephan squintlet. And what it is actually 5 galaxies. 4 of them are actually interacting with each other. 1, 2, 3, and the 4th, they're interacting with each other. This galaxy is actually closer to us, but in the sky, they appear all together. But in reality, these 1, 2, 3, 4 galaxies all interact with each other gravitationally. So here again, you have seen this galaxy is not a part of this 4, but it appears. But these 2 galaxies are merged together, and you can see these 2 galaxies merging. You have the tidal tail, as you see, as these galaxies come towards each other, they strip some of the material, and it's from this tail. This galaxy, the one which is not the part, is about 40 million light years away from us. 40 million light years. So light left that galaxy 40 million years ago. But light left these galaxies about 290 million years ago. They're farther away, but they're all interacting. So that's the closest galaxy. And here's the interesting, if you look at this galaxy over here, and with the James Webb telescope, because it can peer through the dust, you're seeing somewhere at the center of this galaxy. And the center of this galaxy has a huge black hole, about 24 million times the mass of the sun. And the way you can figure it out is because you study the motion of some of the gases going around the black hole. And the James Webb telescope can do that. And by studying the speed of the gases, we can figure out there has to be something massive for these gases to travel so fast. And that's how we have an idea of how massive the black hole is. Here's an example of a planetary, of a star-forming region called the Carina Nebula. This was a picture taken from the Earth. This was taken by the Hubble Space Telescope, by the James Webb Telescope. It's about 7,000 light years away from the Earth. I'll skip this slide, but this is what it looked like. If you looked at the top part of the nebula, this is what it looked like. It's a cavity. You're looking at the edge of the cavity. That's taken with the Hubble Space Telescope. And this picture was taken by the James Webb. See how more clearer it is compared to the Hubble telescope. And if you look carefully, these are kind of pillars of gas. Now, this looks small to you, but light would take 7 years to go from one end to the other end. Light takes 8 minutes to go from here to the sun. Talking about a huge object for light to take 7 years to go from one end to the other end. So this is like the edge of a huge cavity where there are bright stars on the top, hot young stars, and the ultraviolet radiation are stripping away the gases. And that's why you see these streamers out here. These are gases being stripped away by the hot stars, which you don't see. It's above this cavity. Another picture, this is of Uranus. It's kind of this in this color because it has methane in its atmosphere, and methane absorbs most of the red light. So what is reflected back is the bluish green light. This is Uranus, but this picture was taken by the Hubble Space Telescope, sorry, by the James Webb Telescope, and it has detected. We have seen these rings on Uranus before, but this is a far better picture of the rings of Uranus. Again, here's a picture of the rings of Uranus. Prior to that, we had a picture from Voyager, but they were very not as good as this one over here. I'm going to skip certain slides. Here's another interesting object. This is a moon of Saturn called Enceladus. And why this is exciting? Because if you look over here, these are all actually water geysers. These are water vapor erupting from the surface. Below the surface of Enceladus, we think there is ice cold water. And there are cracks in the surface, and this water is being ejected away in the form of a geyser. But look how big this geyser is. One of these geysers is actually extends about 20 times the size of the moon itself, Enceladus itself. It's a huge geyser. Why is this exciting? Because there are lots of places in our solar system. This is another talk altogether that we think there is water, fresh water, and salt water that might harbor life. We don't know. Here, a picture of Saturn's rings as seen by the Hubble Space Telescope, and this is what is seen by the James Webb Telescope. Here's again someone doing this. That is very appropriate. Thank you. Here's the picture of, we can't see a black hole, but here's the farthest black hole ever detected in X-rays. Because black holes are very, very hot, they're mostly emitting X-rays. So we have what is a Chandra X-ray telescope. It's the name of the Indian astrophysicist Chandrasekhar. It looked at the X-rays coming from the black hole. But the James Webb telescope, because it can peer through the dust, looked at the galaxy itself. So this is the farthest galaxy we have seen in terms of. Here's a star which has exploded, and that's a remnant of the star called the Crab Nebula. It actually exploded in the year 1050. But as you can see, the James Webb telescope has a very detailed picture of the Crab Nebula. I'll skip this. Here's another one, the Horsehead Nebula. Here's a picture taken from the Earth. Here's taken picture by the Hubble. And the James Webb telescope looked at this mane of the, it looks like a horse. It's actually a place where stars form, a lot of gases. But you have hot stars around it, which eroded away some of the gases, and the most dense gas areas were left behind, and it looks like a horse. But the James Webb telescope looked at this area on the top, and this is what it saw. Again, with any web images, you can see a lot of galaxies in the background. But here's what you see. This is about 0.8 light years across, less than 1 light year. But it's a huge object. But this is just cold molecular hydrogen gas. The hydrogen gas is kind of locked, the atoms are locked together in the molecule. But as you go above out here, because you have ultraviolet radiation from stars above it, the molecular hydrogen becomes atomic hydrogen. It glows in the red, and that's what you're seeing over here. So again, here's a close-up picture of the top of that molecular cloud. This is amazing pictures. This was by the way, this is the latest picture taken just a few days ago. And finally, if you ever want to know what James Webb is observing, you can go to the website. And this is the one I took this morning. They're trying to observe a exoplanet somewhere out here, but I'll give you more details. If you want to see where it is, you can go to the website. So I'm going to stop here. I almost took more than an hour. And if there's any time, I can answer some questions. But if there is no time, Venkatraman, you can take they can email you the questions. Sure. And you can send it back to me.
Thank you. Thank you so much, Jaideep. That was a fantastic, fabulous presentation. On behalf of all the participants, I convey my sincere thanks to you. There are two questions. Jaideep,
Sure.
can I convey the questions to you?
Absolutely, absolutely.
The first question is from an engineering student. He asks, what is the most important observation of the Webb telescope so far? What is the most important observation?
Well, it depends on the person who's observing it. So, I might have one object which is dear to me, and I'll say that's most important. To me, well, there are two ways to look at it. If you want to look at it a big picture, I think the deep field image is very important because it gives us an idea what the universe looked like, billions of years ago. But if you want to think about, are we alone? Is it possible to have life somewhere else? I would look at this newly forming stars and some newly forming planets, which has evidence of molecules that could form life in the future. So it all depends whom you're asking. It could be a different answer.
Okay.
But to a scientist who's working on that field, that object is very, very important. But from our humanity point of view, I would go more towards finding gases and planets around other stars, because that will tell us life can exist elsewhere. Also, look at the oceans. Look at the ocean. There's a moon of Jupiter called Europa. And Europa, we know 99.9% there is an ocean under the thick ice. For Enceladus, we have seen the water geysers, so we know there is water. So we would like to send spacecrafts to these moons and search for water. So again, as you said, one of the questions we were asking is, are we alone? Are we alone? I don't know. No. For me, I would think with about more than 5 billion galaxy planets in our universe, we should have some planets like the Earth, and maybe there's life on them. But we have no evidence of life elsewhere. Okay, I know we hear a lot of stories of UFOs and aliens, but we have no evidence for it. I'm not saying there are no aliens. I'm not saying there is no life elsewhere, but we have no evidence for it. And as an astronomer, as a scientist, and as a person on Earth, I would love to see that there is life elsewhere. I would love to meet an alien. Who knows?
We understand.
Yeah. And what was the other
Before
question?
I go to the next question,
Yeah.
can I request a few words from Dr. Komati, please? Dr. Komati, please, can I request to unmute yourself, please?
Good evening.
Yes,
I
yes,
love
madam,
you.
please.
Yeah,
Yes, ma'am.
a very, very, very nice presentation, sir, Dr. Jaideep. It is very interesting and it is very inspiring too, with the youngsters to know more about the space. Thank you for it. Thank you. So I'm Dr. Gomati, CSI Society Chair, Chennai. Thank you so much, sir.
Thank you. Thank you, madam. Dr. L.K. Sharma, few words from your side, please. Sharma ji.
Dr. Jaideep, really, yeah. It was great presentation. Really into that. Dr. Jaideep has gone into the depth, and so many things which we never imagined, we can't even think of. You have highlighted all those things, and I think for students you have created the one kind of eagerness that they will all will be searching on Google, what is this, what is that. And thank you very much once again. Thank you.
Thank you, Sharma ji. Are there any questions from the participants, please? Any questions, please? The feedback in the chat box is very encouraging for the organizers. Any specific question to Dr. Jaideep, please?
And remember, no question is a stupid question.
Jaideep, the other question that I have, again from an engineering student, is, has the data from the Webb telescope been converted into commercial application? Has the commercial use of the data started? Is it possible to throw some light on that?
Well, this is talking about astronomy data. So, there's not much of commercial use for this. This is more for knowledge. Now,
Okay.
the commercial part of this is how, for example, the sun shield, or for example, some of the instruments that were built. So they not from the science data, but from the engineering data, what NASA does is it takes the information and gives it out to industry. So a lot of the things that you see in everyday life is a result of space exploration. And because NASA and even ISRO is doing it now, they give all the information out to small companies. The small companies can now take those and come up with products. So in the case of James Webb Telescope, I would think more of the commercial applications would be some of the detectors. And then, of course, I know there's someone out here with starting doing artificial intelligence. So
Yeah.
with the huge amount of data that we are going to get, and we are getting, one way to do it is use machine language to analyze the data. And NASA has been doing it for years and years, but things are getting a lot more better in terms of analyzing the data. So I would think, if you have more data, and I could be wrong, and the person who is the AI expert can correct me, but I think you can, the more data you have, the more you can create better ways of interpreting the data through machine language and AI. So that's the only commercial aspect I can see.
Thank you, Jaideep. There's a question from Mr. Yogeshwaran about gravitational lensing. Could you throw some light on that?
Yeah, it's I said I threw too many things, but it's like a convex lens, what it does, you take the light from the lens and you allow it to go through the convex lens, and it's kind of converges it. It magnifies it, right? You take a magnifying lens and you're reading something, it's magnifying the object behind you. The same thing, the mass of this groups of galaxies, there's so much mass in them that the gravity acts as a lens. This was Einstein, which had predicted it. So if you have any object behind it, then that object is magnified by the gravity of this massive object in front. And actually, if you look at it, it actually has the same object on the back with the 4 images, more gravitational images. The same object, but 4 images. But it's nothing, the gravity is acting like a convex lens and magnifying the object. So instead of a mirror, you have the gravity of the mass between us and a faraway object. It'll take me about 15-20 minutes to explain it properly, but this is the gist of it. And I know I went and talked about that's the problem with, if we talk about astronomy, there's so many, if we don't have a background in astronomy, there are so many things that we have to explain to do that. So that's why my talk takes so long, because I try to explain some of the fundamentals to understand. But yeah,
thanks, Jaideep. Jaideep, there was a question about nuclear space. We hear a lot about that. Some thoughts on that, please?
Yeah, so talking about propulsion.
Yep.
So if you want to get away from the Earth, the gravity well of the Earth, nuclear propulsion, you need a lot of nuclear fuel. That's not possible. There you have to use either chemical fuels like we have right now, or something called maglevs. But once you're in space, and you don't need a lot of fuel, then what can be used for fuel? You don't want to carry a lot of fuel with you. That makes the object heavy. So one thing you do is to carry radioactive material with you, and the radioactive material, it's a small material, and that can generate the power you need to operate your instruments and everything. But the problem is, you have too much of nuclear material in a rocket, and if the rocket explodes, that's a problem. So there is a large group of people which do not like the fact that we have nuclear material in rockets. But that's the reason why we try to launch rockets in places where it's going over the ocean and not over the Earth. So Nuclear propulsion is interesting. It's a cheap way of getting energy. The other one is ion propulsion. They use ions, and we've done that with spacecrafts. Another thing is a solar wind. You can use a solar wind, but again, it takes it'll just give you we need very little propulsion once you're in outer space. So nuclear is a cheap way of doing it, but it's dangerous. So you have people on both sides.
We understand. Okay. Jaideep, you would also encourage questions by email to you. Is that fine? If the
That's
students and others. Thanks for that, Jaideep. Giving due respect to time and all the participants, the webinar comes to a close. Explore the space. Would like to convey its sincere thanks to Dr. Jaideep Mukherjee, Dr. L.K. Sharma-ji, Madam Komuti, and other friends from Computer Society of India, and all other students who have joined for this webinar. Thank you so much. We encourage questions from students and others, and we'll be glad to connect you to Dr. Jaideep Mukherjee, who is a great friend of science and STEM dissemination. Thank you so much, Jaideep. You have been very kind to us, and there are no words to thank you. Thank you so much.
Thank you, Dr. Jaideep.
Thank you, Sharma.
Thank you.
Hope to see you in Florida, Dr.
Thank
Sharma.
you. Thank you very much.
Thank you all.
See you.
Thank you, everybody. Thank you.
Bye. Bye. Welcome.